All right, how's everyone doing? If you can hear me, write a little message in the chat. Cool, thanks. All right, we're going to get started right away because there's a lot to talk about. So welcome back to another lecture on exponential asymptotics for the physical sciences. Last lecture we covered, we're continuing our coverage of example problems, of toy problems to illustrate some of the concepts, and we looked at the complementary error function. So the complementary error function is related to this differential equation here for phi as a function of z, epsilon is a small parameter, and we showed that you can essentially just integrate this function and write it in terms of an integral. We did the analysis of this integral using steepest descents. We're going to recap that analysis, and then we're going to say a few words about how you can derive the same things by studying the differential equation itself. So as I point out again and again, this is an underlying philosophy for how we study some more difficult problems, is to make up problems that you know the answer to and then to derive the root there. Okay, so let's recap the analysis by steepest descent. So this is the integral that you want to study as epsilon goes to 0, and here you want to integrate in the k plane. So k is the integration variable. You want to integrate from a point z to a point at infinity, and the integrand is dictated by the behavior of this function f of k here. The function f has a saddle point, so f prime is equal to 0 at k is equal to 0. So we know that 0 is going to be a special point to be considered. The function is such that it decays at positive infinity and minus infinity. So these are valleys in the function, so I often shade them hatched for a valley. And the idea is that you start off with a point z, and then you have to end up in the valley. And to do that, you follow paths of steepest descent. And the paths of steepest descent are found by taking the imaginary part of this function f. So there are contours for which the imaginary part of f is constant. So for a point z that lies in this first quadrant, you just have to follow a path like a hyperbola towards positive infinity, and in that case you would then derive the dominant contribution of this integral. It would tell you that phi twiddles the integral about the endpoint, so you might write that schematically as the integral about this endpoint. And I'm trying to figure out what it has to be. So in this case, we wrote this as phi base. This is the basic asymptotic expansion, just in epsilon algebraic powers. And in this case, I think it's the leading order is something like e to the minus, let me see here, e to the minus z squared over 2 epsilon squared over z. Okay, so hopefully you can make that out. E to the minus z squared over 2 epsilon squared over z, plus order epsilon corrections and so forth. One of the differences with this problem is that this base series is always multiplied by this exponential factor. So the base series itself is exponentially small for the conventional values of z on the real axis, so keep that in mind. But the asymptotic expansion is always just this exponential times powers of epsilon. Okay. So the way that you can imagine it is also in this z-plane. You're interested in what happens to the function phi as you walk around in the z-plane. And in this case, you've taken a point z here. And for a point z evaluated on this first quadrant, we know that our phi is then asymptotic to this base series, which comes from the dominant contribution from z. Okay? But what we found was that if you then begin to evaluate your z values at other regions of the complex plane, in particular, if you're to cross this imaginary axis, so if I call this situation 1 here, this is situation 1. If I'm in situation 2, so in order for you to travel from a point z, which is now in this upper half location, to the valley at positive infinity, you first have to travel to minus infinity, where there's a valley, and then you have to go up along the imaginary axis, hit the saddle point, and go to the valley that way in order to follow paths steepest descent. In this case, for this situation, you would say that phi is approximated by its regular asymptotic expansion from the endpoint contribution, but then you have to add in a saddle point contribution around 0. And then you would go away and develop the approximation for that secondary integral. And I think in this case it's something like root 2 pi epsilon to this order of approximation. And then we pointed out that, yes, okay, this is not exponentially small, but actually this is exponentially small compared to this series here. Okay? So in this upper half plane, you have phi base plus root 2 pi times epsilon. This is your exponential asymptotics. This has switched on across this line. And then as we introduce this terminology, it's such that this is called your Stokes line. So the Stokes line is this critical line across which exponentials switch on or switch off. By the time you get to the negative real axis, okay, the series actually rearranges itself. The term that you switched on is now dominant over the term that was doing the switching. So along this real axis, you have root 2 pi epsilon plus the base. And I sometimes write it in this way, ordering them in this fashion to indicate which term is dominant over the other. The location where they switch dominance is actually along this line here, which we'd call the anti-Stokes line. It's when this base series is then the same order as the term that did the switching. So if I'm now in the lower half plane, I'm at item number 3 here, then my point z, so remember this is the k plane, this is the integration plane. In order for me to reach the valley at positive infinity, I again have to go to minus infinity along the hyperbola, go up, pick up the saddle, and then go right, continue rightwards towards positive infinity. So in this case, in this situation 3, the series that I have is the same. The approximation I have is still my exponentially small term, though at this point is no longer exponentially small, it's now big, and then the secondary base approximation. And then finally, by the time I get to location 4, I'm now in the positive, I'm in the right half plane here at a point z, and I have to reach the valley at positive infinity, but in this case, I don't have to pick up the saddle point, and I go straight there. So once I get back to this location, I return to myself and I have a consistency. So I return to the point that I started off with. So this is quite nice. Okay? So let me now show you a picture of how you might illustrate this switching on and switching off process plotted on this diagram here. So one way to that, and I think this picture was originally, this kind of illustration was originally done by Stokes. One way is to just schematically draw a curve that corresponds to either the base approximation or the term that's being switched on. So at this location in Z, I have my base approximation. So I would draw that out like this. At this point, I switch on my exponential, and it's small. So I'm going to draw it such that the distance from the origin corresponds to the magnitude of the term. So this is phi base. And at this point, I'm going to switch on my exponentially small term, and they're going to exchange dominances at the anti-Stokes line. By the time I get to the negative real axis, the term that I switched on is now dominating over the original base expansion. And then they exchange again at the next anti-Stokes line. And then once I've reached the lower half of the Stokes line here, the term that I switched on gets switched off. And I continue onwards with just my base expansion. So this one here is my root 2 pi epsilon. Okay? All right, now that's all. This is great. One question that you might have is how can you predict some of these Stokes and anti-Stokes lines? And part of that is you have to go through the exercise to do it. But the idea is that, okay, let's look at this picture here. So in some of the other visuals from the last lecture, I actually plotted for you the surface. So if I imagine the real part of F gives me the surface, because the real part of F gives me the magnitude, I mean, essentially scales that magnitude, that integrand. So what you're imagining is a surface where at this point Z, you're quite high up. And then as you follow the contour down to positive infinity, you're then quite low. And you're following the path of steepest descent towards that surface. Now consider the situation where your point Z moves, and then you are at this Stokes line now. What has happened to your surface? Well, at that location, well, so let me plot it here on the top left here. So if Z lies right on that Stokes line, then at that point there's essentially a steepest descent line that connects Z with the saddle point. Okay? And so at that point, the criteria is that the imaginary part of F of Z has to be equal to the imaginary part of F of the saddle point. And in addition to that, it must be the case that the saddle point, in order for the saddle point to connect up with the steepest descent line from Z, it must be the case that the saddle point is downhill from Z, right? So in this case, you would need the real part of F of Z, right, to be greater than or equal to the real part of the saddle point, so that the saddle point is indeed downhill from the point Z. Okay? This first criteria is the criteria for a path of steepest descent. Right? So this first criteria is what you would impose in order to find these curves across which the paths of steepest descent follow. This is a dominance criterion. So this criterion says that essentially the exponential that's doing the switching has to reach peak exponential dominance over the thing that's being switched on. Okay? Which is essentially just saying that you have now two contributions along your path of steepest descent, a Z contribution, and then a saddle point, and the saddle point has to directly lie along the path of steepest descent, and it has to be lower. Now, what happens when you reach this location here in z, well, at that point, my z point has swung to the diagonal here. Okay, the path of steepest descent from z goes to the valley, as we know, and then it climbs back up and goes back down the saddle. But the fact that the two series are equal, root 2 pi is equal to the base series, is telling you that though they're not connected by a steepest descent path, actually they're the same height. So at this location here, the real part of f of z is actually equal to the real part of f of 0. Okay? So we're going to go on, but we're going to come back to these criteria. We're going to use these criteria again and again. In particular, for the next example, for the Airy equation, we'll see this exact criteria. But the idea for you just to get comfortable with is that these exponential switchings are happening because your key dominant contributions to the integral are moving up and down in the topology that corresponds to the integrand. That as your z point moves around in the complex plane, you may be picking up extra contributions in the integration plane, and that's the switching on and off of these exponentials. We've seen that now for the case of the exponential integral, where the thing that was being switched on was a residue contribution. And we've seen it here where the thing that is switched on is where the endpoint contribution switches on a saddle point contribution. Okay? So now I'm going to very briefly explain to you how the analysis of the complementary area function was done. This is similar in spirit to how it was done in the exponential integral, where you want to study purely the differential equation and then do some kind of optimal truncation and Stokes line smoothing business and derive the exponentials without the integral. I'm only going to do this, I'm going to do it only quite quickly, and you can refer to the notes for the full details. Okay. I'm going to do it quickly enough so that you get an idea of how it can be done. Right, the first thing that we want to do, so we want to study this differential equation now and try to derive all these switchings without the integral. Now before we do that, it's useful for us to scale out the exponential, because we know that the leading order solution for this problem, the endpoint contribution, is basically an exponential. We'd rather have an algebraic series in powers of epsilon so that we can get our usual, phi naught plus epsilon phi 1, or epsilon squared in this case, business. So what we're going to do is we're going to let, this is what's called a Louisville green or a WKB ansatz. So we're going to let this be an unknown function a of z, e to the, I think I use u's in the notes, and I use minus u of z over epsilon squared. And essentially we're going to substitute this into the differential equation, solve for the function u, and then we'll get a differential equation for a, and then this will be, the key is that this a will then go up in powers of epsilon, so then we can do our usual asymptotic analysis. Okay, so if I take one derivative here, I have minus u prime over epsilon squared times a plus a prime and e to the minus u over epsilon squared. And then I take a second derivative. I'll have two powers of this one here, so that's a u prime over epsilon squared times a. And then I have a bunch of, have 2 a prime over epsilon squared. And then I have a minus u double prime over epsilon squared a. And then I have an a double prime. It's all multiplied by an exponential. Okay? So then I have to substitute this equation into that. And if you've done things correctly, if you've chosen your powers of epsilon here correctly, then the leading order problem is going to give you something for u. That's the idea. So if I multiply this quantity by epsilon squared, I'm going to have u prime squared times a minus epsilon squared, so that's plus epsilon squared, then I have a minus 2u prime times a prime plus minus u double prime times a. So I had to multiply everything by, okay, sorry, I multiplied this by epsilon. This is 1 over epsilon to the 4, and I multiply it by an epsilon squared, so I get 1 over epsilon squared here. These are all epsilon squares, so they just become 1 times that, and then I have a double prime times epsilon squared, so that's all from the second derivative term. And then I have a plus z times this one here. So that gives me a minus u prime over epsilon squared times a plus a prime. Okay, and then everything here is multiplied by an exponential, but then it's equal to 0, so you can take away the exponential. Okay, and if you've done everything right, then if you look at this term 1 and this term 1 here, you get basically u prime squared is equal to z times u prime. And I'm going to ignore the constant solution, and I'm just going to have u prime is basically equal to z. So u is equal to z squared over 2. Plus a constant, but the constant I can absorb it into the definition of a just because of how the exponential works. Okay, so fine. And then so what you do then is you basically substitute this u into the remaining terms, and then you're going to get a differential equation for a. And the key is that that differential equation for a is then just developed as a regular power series in epsilons. So that's a bit more familiar to us. Okay, so we can make that substitution. And then we see that the analysis of this differential equation is then equivalent to the analysis of epsilon squared times a double prime minus z times a prime minus a is equal to 0. So this is our new problem. And then the key is that now when you expand a into powers of epsilon, you see so if I write a then as a naught plus epsilon squared a1 plus so forth, I'm going to get a naught is 1 over z. It's actually a constant here, but you can show that this constant, in order to satisfy the boundary conditions, should be 1. And then you get a1 is a naught prime over z, so that becomes a minus 1 over z, a naught prime squared 3, and so forth and so on. And in fact, in general, you can just check that an is equal to an minus 1 prime over 2. Okay. So what you're seeing is this prototypical behavior that we've seen many times, which is that our leading order problem has a singularity at z is equal to 0, and then you see that because the subsequent orders all have to differentiate this leading term, that singularity will magnify in strength. You're going to always end up with some kind of factorial expression on the top, and then a power expression on the bottom. And in particular, you can show that an is, in the limit that n goes to infinity, it's going to diverge in the form that we have started to try to get accustomed to, which is what's called a factorial over power expression. We're using, instead of the factorial function, we're just using this gamma function. And in this case, chi of z is equal to minus z squared over 2. And then gamma is equal to 1/2. And lambda is equal to I over root 2 pi. Okay. Now, there are two ways to figure out how to obtain these kinds of expressions. The first way is basically you take this expression here, and then you just keep on iterating it. So you take a derivative, divide it by 2, and that becomes the next one, and so on and so forth. So you'll see that I end up with having a 3 here, 3 that comes down, and then it will be a 3 times 5, and 3 times 5 times 7, etc. The other way to do it is you make this assumption that it follows this form, and then you try to substitute this into this expression, and then to figure out what the components have to be. So I'm going to show you how to do that now. But you can also refer to the notes and see that you can attempt to derive the form just by looking at the expression, the progression of the terms one by one. Obviously, this route of just looking at the progression of terms only works because it's a sufficiently simple problem that you can solve it order by order in this fashion. But later on, for more complicated problems, we'll see that this route works quite well. That if you can guess what the form is, you can substitute that form into the equation for an, and then hope to try to derive, even for nonlinear problems, try to derive the necessary form of divergence. Let's see how it works for this problem here. So for this problem, I have an is equal to an minus 1 prime over 2. And I'm going to make the assumption that in the limit that n becomes large, my an is going to behave like this factorial over power form. For now, I'm making the assumption that this gamma and this lambda are just constant. But in general, you may, for more complicated problems, this will certainly not be the case. This function should be a function of z itself. For this case, it is constant. And so for simplicity, I'm just going to assume it to be as such. So now I have to take a derivative of this function. So this is an prime. And again, just to reiterate, for this problem, okay, so for this problem, I'm assuming my lambda is constant. I'm just going to take a derivative. So I'm going to have a minus n plus gamma that comes from this, from the differentiation of this denominator, times a chi prime. And then I have to differentiate, well, actually I have to, that's all I have to do, because this is the only function of z. It would have been a little bit more complicated if I had a function in front here. Okay. Now I can use the fact that n plus gamma times the gamma function is actually equal to gamma function of n plus gamma plus 1. And so that allows me to simplify this expression a little bit. So I have, in this case, lambda times gamma function of n plus gamma plus 1 times chi prime. And then now I can put this expression into the recurrence relation. And you notice the correct shift here. This is now an n minus 1, but then if I put n minus 1 into this expression here, I'll have something that looks almost identical to the line on top. So now the recurrence relation will tell me that I have lambda times gamma function of n plus gamma over chi of n plus gamma is equal to lambda of gamma of n plus gamma over chi of n plus gamma, but I have a chi prime here. And I had a typo in this expression because this is not actually an minus 1 prime over 2, is an minus 1 prime over z that I just realized. So this is over z. And then now this gives me an equation for chi. So you see that chi prime is equal to z. Now this chi prime, this chi is the function that generated the divergence. So you need it to be 0 at the point where there was the origin of that divergence of your asymptotic expansion, in this case, is just 0. So chi should be 1/2 times z squared. My z looks like 2's. 1/2 z squared plus a constant, and I need chi of 0 to be 0, and that tells me my constant is 0. So you see, I have managed to derive the form of the divergence just by substituting my guess for the form into the recurrence relation and then trying to extract it out order by order. I'm doing the analysis here in the limit that n tends to infinity, but for this problem for which the recurrence relation is so simple, you haven't really used the fact that it does so in the limit that n tends to infinity. Okay? All right, so you have now developed the equation, you've developed the base asymptotic expansion for A, you have predicted the form of the divergence, so you've developed most of the ingredients you need to derive the exponential asymptotics. Okay? In particular, you can now let A be your asymptotic expansion. In this case, it's going up in powers of epsilon squared instead of epsilon because the equation is being forced by epsilon squares. This is an. You can now truncate this and examine the remainder. And again, you're going to end up with a linear equation for the remainder, but the right-hand side of this remainder is going to be forced by the late terms. Just as it was for the exponential integral. So you substitute this into the equation. Here I've written the equation for phi, but it's actually the equation for A that we need. You get your linear equation for the remainder, and then you'll have something that you're left over with on the right-hand side because you had to truncate the series. And then now you get to use that factorial over power divergence. And if you do that and you follow exactly the same steps as we did for the exponential integral, you'll be able to predict the necessary switching on that we predicted from steepest descents. Okay? I'm going to, we're eventually going to give you the general recipe for how to do all these things, but we're going to stop the problem here for the complementary area function. So long as you know there is this recipe, we're doing it for a case-by-case basis, but actually in the next couple weeks and couple lectures, we're going to want to give you the general recipe for all kind of ODEs, all nonlinear ODEs. Right? So how do you derive these exponentials? How do you develop the late terms? All that business. Okay. What we want to do now in the time that remains is to go and look at the Airy equation. And the Airy equation, I think, will be the last kind of standard example before we go on to more complicated examples. The Airy equation is like the complementary Airy function. It's a second order problem. It's got exponential asymptotics in it. It's special because you might say that the Airy equation was the origin of exponential asymptotics because Stokes a long time ago had struggled to study this particular problem. For reasons of pedagogy, I typically don't present the Airy equation as the first example you come up with because it's a lot harder to study than the exponential integral. But now that we have our techniques of steepest descents and we sort of know a bit better what's going on, we can now go back to look at this original problem that Stokes had studied in the 1800s. Okay? All right, so let me see if I can You can hear me now, can't you? All right, I see what the issue is. Let me see if I can sort this out. All right, can you hear me now? Yeah, okay. So I just had the wrong source. All right, so okay, so as I was saying, this is a famous problem because Stokes, who was one of the great mathematical physicists in the 1800s, had discussed this problem extensively. So this is a letter that he wrote from to his fiancée in the mid-1800s that you can look up, and is found in many of his books of correspondence. So he wrote, "When the cat's away, the mice may play. You are the cat, and I am the poor little mouse. I've been doing what I guess you won't let me do when we're married, sitting up till 3 o'clock in the morning, fighting hard against a mathematical difficulty. Some years ago, I attacked an integral of Airy's, and after a severe trial, reduced it into a readily calculable form. But there was one difficulty about it which, though I tried till I almost made myself ill, I could not get over, and at last I had to give it up and profess myself unable to master it. I took it up again a few days ago, and after 2 or 3 days' fight, the last of which I sat up till 3, I at last mastered it." Okay, so what was the problem that he was trying for many years to master? Let me present it to you in this way. So this is the differential equation, which we now know is the Airy equation. Okay, and so the Airy equation is the second order differential equation with basically decay conditions at plus or minus infinity. So it exists along the real z-axis. Okay, now Stokes was only considering, initially for real values of z here. And he was also considering an integral form of this differential equation, which I'm going to present to you soon after. But for reasons that we're interested in, I'm going to explain to you the problem as it pertains to the differential equation. Okay. Now, this you're essentially trying to develop approximations to solutions y as a function of z. This is a problem that you can't solve in closed form. And one thing that was known by Stokes is that if you try to do the Taylor series approximation about z is equal to 0, it does not work particularly well at all to describe the solutions. Now, the graph that you see here is the numerical solution, or it's one of the two linearly independent solutions of this equation, which is known as the AI function, the Airy function, or Airy AI function. There's also an Airy BI function as well. But what Stokes was wondering was how to develop an approximation to this solution, and indeed by using the analysis that we had presented earlier, this kind of Louisville green or WKB analysis, he had developed an approximation to the blue curve that you see plotted in red and then plotted in light green. Now, the red one, let's focus on that one for now. This is an exponentially decaying solution. You see e to the minus 2/3 z to the 3/2. And just to clarify, these are solutions that are formally asymptotic approximations in the limit that z is large. Okay, we've been looking at epsilon small problems, but these are solutions which are valid as z goes to infinity. Indeed, you see that it matches very well. The red curve matches the blue curve very well for even moderately small values of z. It matches quite well. Okay. The other thing you'll notice is that on the left half of the plane, there are oscillations. And one can think of the oscillations as two exponentials. So I can write this as in the form of a cosine, but for reasons that are soon to be clear to you, I've written them in this way involving two exponentials. Okay. Now, the puzzle that Stokes was confused about is as follows. I can take my solution, my WKB or exponential solution on the right here, where y twiddles 1/z to the quarter times e to the minus 2/3 z to the 3/2. And obviously I cannot pass through the origin in my approximation because I'd be going through a singularity with z is equal to 0. But what's stopping you from considering this in the complex plane? So the axis into the page now is the imaginary part of z. And what's stopping you from just simply taking your approximation, which is valid on the right here, this exponential decay, and then moving it until you get to the left? There doesn't seem to be anything that has violated this approximation throughout this process, right? You've not traveled through any kind of singularity. And yet, why is it that when you're on the left, you have it's paired? It's paired exponential. So the first one you began with was e to the minus 2/3 z to the 3/2. On the right-hand side, where the red curve is valid, you had to discard the second exponential because it's exponentially growing. But you see that by the time you get to the left-hand side and the negative real axis, you have the left exponential. And indeed, if you add the two together, if you add these two solutions together, you'll develop the cosine. Okay? So this was essentially Stokes' question. Why do you have one exponential on the right, but you have two on the left? And the answer that we know now is that there is Stokes phenomena going on. That my approximation on the right is indeed this exponential decay term. But as I move around in the complex plane, at some point I'm going to switch on the secondary exponential. Okay? And Stokes had done this analysis with the integral equation. So this is what we're going to present to you is, again, let's think of the problem using steepest descents. Okay? So I can take the differential equation, and again, this is something that you can refer to the notes. I do it in the notes. You can essentially Fourier transform the problem and then write it in terms of an integral. So there's a way for you to convert from that second order differential equation to an integral equation. And the integral equation looks as you see here. It's y is a function of z is this integral over a contour to be stated times e to the function f of w over epsilon, and here w is my integration variable. Okay? Now, firstly, this contour has to begin from essentially a certain angle. I think it's minus something like minus 2 pi over 3, and it has to tend towards 2 pi over 3. I have to double check what those angles are. But it has to move from a wedge somewhere in the lower half plane to a wedge somewhere in the upper half, into the left upper half plane. Okay? And so it has to go from a valley, from a start valley to an end valley. And these valleys you can essentially derive just by looking at where the exponential has to tend to in order to decay in W. Okay? Now, notice as well that the exponential argument here, f of w over epsilon, okay, it has the point z in there. So z is a parameter in your argument. Okay? And the idea is, as we know, we're going to use steepest descent on this problem. In the limit that epsilon tends to 0, we want to deform the contour of integration, which goes from the start point to the end point in a favorable way. Hopefully through the saddle points of f, or through other critical points. So you can take your, this is what the statement says, let's approximate this integral using steepest descents, and let's go and find where our saddle points are. So we're going to take an f, take f prime of w equal to 0, and then set that, and then solve for our w. And we see that w, the saddle points, are given by plus or minus root z. Okay? So this is the picture that you might have in your head on the top right here. You're integrating in the w plane from the start point to the end point, and as your z value varies, z is where the function is being evaluated, your saddle points are moving. Okay? And they're moving in this way where you essentially have the angle of the argument of z, and then it scales with the magnitude of z, in essence. Okay? So what we want to do then is basically consider what happens when our z value starts to move around in the complex plane. We want to find out, okay, if z is real and positive, which is equivalent to here on the right, hopefully we have a contribution to the integral which corresponds to Stokes' original exponential decay term here. And then what we want to see is that when z begins to rotate in the complex plane, somewhere along the line, you're going to switch on your subdominant exponential. Okay? So here's the steepest descent analysis. Okay, what kind of pictures are we seeing here? On the top left picture, that's the complex z-plane. So we're going to start off along the positive real axis at that red point. Okay? And then on the right picture is the integration plane. Okay? And so you see that I need to go from a valley marked with the start and end up with a valley marked at the end. So those are indicated by dark regions in the contour plane. And I'm simply going to deform my contour, whatever contour I began with from the start to the end, I'm going to make sure that it deforms past the saddle points. And in this case, the saddle points are the two black points that you see on the right graph. So they're located at basically plus or minus 1, I think. Plus or minus root z, sorry. Plus or minus root z. Okay? So this contribution 1, what you then need to do is you need to do a little steepest descent argument about the contribution to the integral from 1. So that's what you're seeing on the lower right element here. Let's let our integration variable be minus root z plus a little vertical element, I times t, because we're walking vertically. You substitute that into the integral, apply your usual Gaussian integration, and then out pops the desired saddle point approximation, which is the approximation that Stokes has developed. Okay? All right, and then now you know what the name of the game is. You're going to then move the z, which is indicated by the red circle here, around the complex plane and see how the right picture is going to deform under that analytic continuation. So now I move z to the dashed line, which we've called the anti-Stokes line. And you see the criterion according to the complex W plane is that at this anti-Stokes line, the two saddle points are equal in height. They're lying at equal height. But there's no need for you to traverse from 1 to 2. And you just simply continue on in your path from the start valley to the end valley. So this anti-Stokes line is not doing anything. Okay? By the time you rotate now to the Stokes line, the integration situation looks as follows. You have to start from the start point and end at the end point, but you're at a critical juncture in which the secondary saddle is exactly along a path of steepest descent. So you basically start low in your valley at the start point, you go up to point number 1, collect that contribution, and then descend to point number 2, collect that contribution, and continue on to your valley. So from that point on, let me go on, I'll go back and cover what that animation appeared. From that point on, in order for you to go from the start point to the end point, you have to collect that item 2, that saddle point. Okay? Well, what's the criteria for this critical Stokes line? Well, you see that in the lower right here. Okay? So the criteria is that the first saddle has reached maximal dominance over saddle 2. This is necessary because saddle 2 has to be downhill from saddle 1. Otherwise, you don't need to go through saddle 2. So at the point where this special curve in the z-plane exists, the secondary saddle is downhill from saddle 1, is exponentially smaller than saddle 1, and it's also linked by a path of steepest descent. So that's the two criteria that you see here. The imaginary part of f evaluated at the first saddle is equal to the imaginary part of f evaluated at the second saddle, and this is the constant phase line. This is the path of steepest ascent or descent. And then the secondary criteria is guaranteeing that it's a path of steepest descent, that the real part of f at the first saddle is greater than the real part of f at the secondary saddle. Okay? And in this case, now we have the Stokes phenomena, and you can go and derive what that contribution has to be, and it essentially looks like this. You have simply switched on z to the 3/2 over epsilon. You've switched on the exponential pair, and you can also verify that the switching, this is not meant to be obvious, you can verify that whatever the number in front of the first exponential was, when the switching occurs, it's the same number multiplied by I. Okay, and that's not meant to be obvious at all. By the time you get to the negative real axis, here illustrated on the left, this is now the anti-Stokes line. And as we said, the anti-Stokes line is a location where both saddles now have equal contribution. They're at the same height. So you imagine the contours here, or you imagine the surface that these contours are trying to represent. You go from a valley here in the dark region up, collect your first saddle, then go back down to another valley, and then you climb back up, collect the second saddle, and go back down to the other valley. But at this location, the two exponentials are actually equal in magnitude. And that's why you end up with a real oscillation on the left. Otherwise, you wouldn't end up with a cosine if it didn't work out to be this way. Okay? And then finally, so here I've written the asymptotic solution. They now have equal footing. The two exponentials are of equal magnitude, and you can massage their form and show they produce a cosine. So now you cross the Stokes line in the lower half plane, and you see that in order for me to go from the start point to the end point, I'm moving towards a situation where this first saddle point 1 has switched off the contribution from 2, or vice versa. And from thereafter, in order for you to go from the start point to the end point, you only need the secondary saddle. Okay? Look at the diagram on the left here, and I want to just also introduce you to the notation that I'm using. You'll see under the labels here, I have 1 equal to 2. Okay? And the notation that I'm using is essentially looking at, so 1 equal to 2 is fairly obvious notation. At the location of this point, the first saddle has equal contribution to the second saddle. So 1 is equal to 2. It is such the case that at this point, 2 doesn't actually exist. Right. At the Stokes line, remember the criteria for a Stokes line is that the saddle point has to reach, saddle point 1 has to reach peak exponential dominance to saddle point 2, because it has to be downhill and it has to be connected by a steep descent line. So that's why we use this notation of 1 greater than equal to 2, 1 greater than 2. And you can also interpret this notation as 1 switching on 2. Our 1 saddle has switched on the 2 saddle. This continues on, and then the next point, 1 is equal to 2. The 1 saddle is equal to the 2 saddle. And then now I'm about to enter a situation where 2 switches off 1. The 2 saddle has switched off the 1 saddle, and at that point, I only have the 2 saddle. Okay? So that was a lot to cover. I mean, it's not a lot to cover, but you can kind of see how we needed these techniques of steep descents to understand this mechanism. Stokes had described, by the way, maybe in the next lecture I can show you more of his original quotations, but Stokes had described this phenomena where an exponential seems to arise, out of nothing. He described it as coming out of a mist. He described it as the secondary exponential seems to emerge as if from a mist, and it's quite poetic, and that's why a lot of authors, after we realized the consequence of what Stokes was pointing out, a lot of authors discuss this original finding. You should appreciate that because we have the method of steep descents, how easy it is, relatively easy to see this mechanism, right? If I go back to this original picture, it's now easy for us to see that as we move around in the complex z-plane from the positive real axis to the negative real axis, somewhere along a line, this Stokes line, this secondary exponential switches on. Our second saddle point is required in order for us to go from one valley, from the start valley to the end valley. But you can appreciate how difficult this must be without this technique of steepest descent, if you didn't think about deformations of integrals in the complex plane. And so ultimately, we return back to this original question of how could you have ever known this really interesting process just by purely looking at the differential equation? And that really is the magic, right? I mean, I think that the basic answer is it's really hard to look at the differential equation and to know that this kind of phenomena occurs. Once you have studied the integral approximation and you have kind of made this connection, you can then use your techniques of exponential asymptotics and derive exactly the switching, and that's kind of what we want to do. We want to study the differential equation itself. But without that intuition of the integral, it's quite hard to do. Now, the payoff of developing your techniques of exponential asymptotics is that you basically begin to recognize the pattern. This pattern of when an exponential is switched on, if you only had the differential equation, in fact, if that differential equation was something even more complicated, like a nonlinear ODE or a PDE or something that you can't even hope to write as an integral equation, you still have a set of tools that will allow you to develop those exponentials. Okay, that's going to leave it at that. We've covered this beautiful Airy equation example. In the next lecture, I'm going to go over and again tell you how to do some of the analysis of the Airy equation. We're not going to go through all the details, but tell you how to do optimal truncation and Stokes line smoothing for the Airy equation. It is essentially the same kind of techniques that we did for the complementary error function and the exponential integral. It's the basic ideas of trying to develop the divergence series, estimating the divergence, and using that to give us the insight of the necessary switching that's going to happen. And at that point, I think once we cover the Airy equation, we're basically done these examples where we have access to the integral, right? The more complicated examples, so this course is exponential asymptotics for the physical sciences. We have to give you some examples from the physical sciences. The Airy equation, by the way, comes up in optics. But there are lots of examples from fluid mechanics and other things that we want to cover. Those problems are going to be nonlinear ODEs and nonlinear integral differential equations, problems where you don't have an integral to deal with. And so once we have developed enough insight, we can then use our techniques to study those kinds of problems. We'll leave it at that, and I'll see you next time. Thanks.